Welcome. I think today we have a joint meetup. We have storm chasers and we have scale warriors here. Scale warriors are engineers and entrepreneurs who are pushing the limits of scale, doing what has never been done before. We're very happy today to have Ron Bodkin, who is founder and CEO of Think Big, join us and talk about Storm. He's one of the pioneers who actually used Hadoop and Storm and all these NoSQL technologies when he was VP of Engineering at Quantcast, and now runs one of the leading consulting houses in the space. So, Ron?
Thank you, Monica. So it's my pleasure to speak here tonight, and definitely great to have a chance to talk a little bit about Storm. As Monica mentioned, what we do at Think Big is we are a services firm that's purpose-built to help companies get measurable value from their data using big data techniques. You know, the broad context is that there's been this tsunami of data coming in, massive amounts of data, more complexity, more opportunity to create value out of data, and it's created this pressure that companies that have been using traditional architectures with older data processing and storage techniques have really hit a breaking point that there's too much opportunity to use data in new innovative ways with scale-out architectures and open source technologies. And we really believe that that's remaking the landscape of storage, of processing, of analytics. And today I'm happy to talk to you a little bit about Storm and how that fits in. And in a context of what we're doing at Think Big with our customers. At Think Big, since we started the company 3 years ago, we've worked with some fantastic companies, technology pioneers, online companies, retailers, financial services, companies like Facebook are customers, companies like NASDAQ, who we spoke with recently, Kantar Media. So we're working in the range of innovative companies that have massive amounts of data, a lot of complexity in their data. And what I want to share with you today is a little bit about what we see, how we see Storm fitting into the picture, so especially and real-time analytics, the role for that. Our approach at Think Big, we work with customers through the life cycle of how they can get value from data. So we help them with Imagine services to think through what are the use cases, where's the value in big data. So often we see companies that take more of a bottoms-up engineering approach of putting up a technology and then trying to figure out how to create value. And we really think you need to come with a use case and a viewpoint of what are we going to do to create value? What are we going to do with this data? How do we drive results? We help with training, and we help with fast, iterative implementations. So that's our approach. And this being a meetup, I'd be remiss if I didn't say that we're a fast-growing company and we're hiring. So definitely, if you're interested in what you hear today, would welcome to hear from you on that front as well.
Where are you located?
So we are located in Mountain View, just a short distance up the road here on San Antonio. And we also have offices in central, so in Utah, Chicago, Boston, and New York. But 99% of you here are in the Bay Area, and our headquarters are here in Mountain View, and that's about half the company. We're about 50 people right now and growing fast. So what I'm going to talk about a little bit is, firstly, before I do that, let me have a show of hands. Who here has worked with Storm already? All right, who has at least played with it or read a bit about it? All right, who's pretty new to it? All right, so it's good. I've got a little bit of a refresher on some of the basics of Storm. What is it? Why is it? I'll talk a little bit about when it's appropriate. I'll talk a little bit about some of the different options for programming it. And then the bulk of the talk is going to be more about applying it. How does it fit into a bigger context of big data? What are some of the characteristics? What are some of the use cases we've seen from customers where we're working and applying it practically? So I guess two other questions. Who here has worked with Hadoop? All right, and who here has worked with a NoSQL database like Aerospike? Okay, great, thank you. So let me give you a little bit of an overview. Storm is fundamentally a system that's designed to let you process streams of data on an ongoing basis. So in a very coarse way, if you know Hadoop and you think of MapReduce, it gives you something like the ability to apply MapReduce to an ongoing stream where you're continuously computing results. Right, so it's give you that directed acyclic graph processing. It's open source. It was created by Nathan Mars initially when he was at Backtype, then adopted it in a lot of contributions made while he was at Twitter and by the folks at Twitter. He's recently left to start a stealth mode startup, which he's not talking about what he's doing. It's designed to be reliable and that you have at least one semantics in how it does its processing. It's written in a Java virtual machine language closure for those keeping score. And the basic notion is that you've got a topology of different elements. You have a spout that's feeding data in, and then you have bolts that feed calculations from one to the next. So it's not really a queuing technology, but a very common approach, as we'll see, is feeding data from a queue into a storm topology. So it's really more of a distributed computation system. The actual placement of the data at rest, data movement is typically being done outside, and the data movement within the storm topology is just for the purposes of doing a calculation. It's related to some other systems. S4 from Yahoo is a similar kind of open source system. Notably, Yahoo's doing a lot with Storm these days, so I think they're embracing it much more. And a lot of precursors in complex event processing systems. So certainly on Wall Street, in the financial world, there were a lot of proprietary systems that would process streams of data, typically not in a scalable model, more of a model of having a single machine, big machine taking a stream of data, or an embarrassingly parallel split of data that different machines worked independently. No technology is perfect. Storm is a couple of things. One is that it is not as easy to dynamically rebalance. So the topologies and cluster sizing is fixed when you set up the environment, so it can be a little bit messy if you want to dynamically adjust on the fly. And then there is a soft single point of failure in the architecture, what's called the Nimbus, which is the coordinator. If that fails, your cluster doesn't go down, but you lose resiliency. You want to recover it so you can recover from other failures. So you're not like red alert panicked if the Nimbus crashes, but you don't want to have that ongoing. And we see strong community support for Storm and a lot of emerging commercial support. I know, for example, one of our partners, InfoChimps, includes Storm and has commercial support for Storm in their platform. And we know of other companies that are working on Storm and intending to have support, but I'm not aware of anyone else that's formally announced commercial support for Storm. Am I late on that? Is there anyone else, any other company you know of that has commercial support for Storm at this point? Well, I'm going to guess this would be the audience to find out if there were. So I guess I'm up to date. Yeah?
Quick question. If it's based in Java, what about garbage collection? I mean, it's a real-time system, basically, so how does it avoid hiccups?
So one request I had was, while I love the interaction of Q&A during a presentation, because we're filming, we want to ask for the questions to be held at the end, and we'll run a mic around. So hold that thought, and we'll get back to that. Good question. For those listening on the recording, they didn't hear it, but it was a good question. You'll hear the answer later. So the basic concepts of Storm, there's a few simple kinds of processes that run in a Storm cluster. You've got the Nimbus, which is, again, that coordinator. You've got the use of Zookeeper as a distributed coordination service. Zookeeper is it's an Apache project. It's part of the Hadoop ecosystem. It gives you a basic building block for having distributed systems coordinate effectively, and that it allows you to have easy ability to have the different workers running. So you have a supervisor process on each machine that's running Storm that's responsible for keeping workers up and running. If something crashes, it can restart them, and the coordination among the distributed pieces is done through Zookeeper. So other than that Nimbus, everything else is fault tolerant and highly resilient. And then talking a little bit more about the concepts in Storm, you've got this notion of putting together an assembly, what's called a topology, which is a way of processing data. A topology in Storm is roughly like a streaming version of a data processing pipeline in MapReduce, a series of processing steps that produce an output. You've got this notion of a stream, which is an ongoing set of data that's coming in, a set of tuples. And a tuple, of course, is a basic notion in math of something with n fields. And that's the basic data type in Storm, the notion of having a number of elements. And of course, you can put anything in one of those tuples. It can be any number of bytes, so you can pack nested data structures, et cetera, in. You've got the notion of a spout, that is something that's feeding data into Storm, and then a bolt, which is something that takes input and potentially produces output. There's no real notion of a sink, something that just writes data out. In practice, a bolt can act as what we would think of informally as a sink, something that it accepts data, just writes data, doesn't have any downstream consumer. But there's no formal notion in Storm of a sink. And then there's a number of useful things. One of the more powerful things in Storm is it's got built into it the ability to move data in common ways. Just like in MapReduce, one of the powerful things is that connector between the map and the reduce phase where you shuffle and sort. In the same way, there's a notion of shuffling and projecting things together, collecting things together with a common value on a field for grouping data. So Storm has the ability to group data in the topology. And so in that way, it's very much a kind of streaming version of what you might think of as MapReduce. There are clearly some differences in terms of what it means to do things like join in a real-time system. There's also a notion of a higher level abstraction in Storm, Trident, which gives you a language to work in terms of higher level data flow. So a little bit like using Pig instead of Java MapReduce in the Hadoop world. So a higher level way of describing data flows and giving you some useful features like specifying exactly one's semantics and making it easier to, for example, join things together. So with that about Storm, a little background on Storm underway, let's talk about, what do we mean by real time? Well, real time is, of course, a concept that's very relative. That in some broad sense, it means something with low latency, that it doesn't take a long time to get an answer. But there's a lot of different notions of what is latency, and there's a lot of different viewpoints of what's low latency. In one of the domains we'll talk a little bit about in financial services, what you see is that a lot of times they think of low latency as nanoseconds, high frequency trading where you're executing trades and being a few nanoseconds ahead of your competitor to seize an opportunity to buy something that's cheap or sell something at a high price is all the difference in the world. For most of the systems we're talking about, certainly Storm is more tuned to the range of human scale real time, which means a couple of seconds, a little bit of latency. But there are cases where you see organizations where they think of real time as anything that happens during the day. It's an hour later, that's real time, right? So Storm plays all the way down to even milliseconds of latency, not microseconds or nanoseconds. And some of the different latency questions you might have are, how quickly can you get an answer to a query? If you want to get some data out of a system, how fast does it come back? Some of the notions would be, how up-to-date is the data in the system at all, right? How frequently is the data refreshed? Do I have data from 2 seconds ago or 2 years ago, right? And indeed, another version is just an end-to-end response of anything, processing a transaction, answering a web interaction, et cetera, right? So people have different notions, but we'll talk about a number of different elements of real-time processing and sort of where Storm fits in. There's some notable areas like certain kinds of query processing, but traditional or alternative technologies are perfectly good. And there's some simple cases of real-time transaction processing where Storm maybe isn't necessary. So I'll try to put it in a context of where it is useful, where we see it providing value, as well as talk about cases where maybe it isn't necessary. So why real time? One of the things that people, one of the main reasons why people like to have real time capability is having a better end user experience, right? So being able to, when you interact, when you show an ad to somebody, you can sort of immediately see what's going on in the system, see a counter, verify what the system's doing, have some confidence in what's going on, a powerful thing, even from a metrics or operational intelligence standpoint, right? So being able to interact with, understand how the system works, that's valuable. Likewise, if you think about when you've got a system that's operating, if you want to understand what might be going wrong or what's happening, you don't want to usually wait for a periodic report to come out. You want to know kind of, even if it's not as accurate, right? So being able to do some amount of analysis of the system relatively quickly, and more generally responding to events, right? There's a lot of cases where if you look at content on the web, the half-life, sort of half of the content gets consumed often within just a few hours. So knowing what's going on during the life cycle of, say, a story that's put up online or a trending article can be pretty important. So having real-time information about that, being able to respond as it's going on, is very important. So those are some examples. But generally, what you see is that I do think it's fair to say that there's a lot of times where real-time is one of these things that actually just always sounds like the right thing to do. And there's a lot of cases where you can say that there's a lot of value in having a little bit more latency, right? So more often, in a sort of sense, why real-time? Maybe the better question is why not always real-time, right? And the reality is that there's more cost and complexity in doing things with real-time. The lower latency you strive to achieve, the more complex and resource intensive it is. So there's a lot of cases where people aren't needing to act on data on a moment-by-moment basis, but having data that's an hour old is dramatically better. I mean, so often when we're working with enterprises, they have data processing systems where data is weeks old before it's finally available. And going from weeks to 1 hour old is a lot of the value of going to real time. That's why those are organizations that think an hour old is real time. But Storm does let you kind of get into that milliseconds and seconds of latency, and there are definitely cases where that's valuable. So, why use Storm? Well, fundamentally, Storm gives you a lot of good stuff in the box that you don't have to build on your own, right? So it gives you a scalable way to manage the queues and the computation. You think about it, as you start to do more and more advanced things in any processing system, you want to have a framework to scale it and manage it and operate it. Very much like, why do people use Hadoop? Well, because it lets you scale the processing of data, the storage of data. In the same way as you're starting to do more things at real time, being able to process, scale the way you do the calculations in real time becomes highly valuable. It's got some good reliability. It's got some nicely tuned performance that's really been proven at massive scale at places like Twitter. It scales. You can process 1 million messages a second on 10 nodes. It's got a vibrant open source community with some real traction. It's starting to get meaningful integration into a number of leading systems. Like a great example at the Hadoop Summit, they announced that you can now use, there's now, Yahoo's contributed an adapter to use Yarn to manage Storm, so that you can execute Storm managed inside of a Hadoop cluster as part of that same cluster of machines, which is interesting. There's a number of programming options for Storm. The most basic one is there's a Java API that's kind of low level with tuples and raw computation. I mentioned that there's a higher level domain-specific language with more SQL-like primitives for data flow for organizing Storm. It actually is it's still Java, but it's a set of stylized method calls that you can use. And then there's a number of other language adapters and DSLs, either within the JVM or put to the side where you have a separate process. So there's ones for Python. There's a couple of different ones, Redstorm and Wukong for Ruby. There's a DSL, of course, in Clojure. Misspelled here, I'm sorry. And Trident ML and even Storm Esper, where Esper is an open source CEP system that uses a SQL syntax. Storm Esper lets you embed that inside of a Storm topology if you want to express calculations there. Although, this is often the case, if you take something that's designed for single machine processing and it has a certain model of state, putting it in a distributed system doesn't magically scale the hard state problems. You still have to find your own way of rolling that. So it's not magic. It just gives you some syntax. So we'll talk about a few different use cases here today. Some of the ones that come to mind is there's a lot of cases, as the title of the talk suggests, where you want to scale a pipeline of data analysis. You want to analyze data in real time. You want to be able to do it where you don't have a single thread, a single machine as a bottleneck. You can harness more resources to get results faster and more predictably. Lively statistics, being able to keep various kinds of counters and statistics on a system, being able to manage the update of that and the retrieval of that is another common one. We'll talk in some depth around the use of this for recommendations, where you want to create recommendations for a user or customer in real time. Needless to say, when you're making recommendations, if somebody asks or you're rendering a page, you want to be able to show them something quickly. Also better predictions, being able to do predictive models in your real time. Real-time analytics in general, not just statistics, but other forms of analytics that you want to understand better in real time. Even online machine learning. We're not going to talk a lot in detail about that, but the notion of being able to update, train. I mean, the simple thing that we will talk about is updating the scoring of a machine learning model in real time, where you computed a fair bit of that model up front, but then you want to do a near real-time update of that data based on what just happened. That's common. A more advanced would be online machine learning where you're actually redoing the training in real time. And there are certainly some experimental things. We're not going to talk a lot about that today, but that's one that's come out. And distributed RPC is a general mechanism of being able to distribute procedure call, aggregate data from many machines and pull results back. Where you're partly using the ability to have a large pool of memory across a node of machines that can do calculation. So taking a look, an overall architecture, this example from the following slides are really examples of different projects, different places where we've applied Storm, because I wanted to give you a kind of a complementary view to, you could go to the GitHub project for Storm and look at some of the well-written documentation and examples and get a feel, but how does it fit into a bigger picture, and what are some real-world cases that are maybe outside of what a Twitter is using and some of the other cases that have been presented in past here at Storm and at other Storm user groups. So one of the things we see is a lot of times we do see Storm being tied in with a number of different technologies. So some different queuing technologies, the ones one of the more popular ones that we see is the use of Kafka, an Apache project that was created by LinkedIn. We'll talk about at least one of the projects where we were doing on Amazon Web Services and used Amazon's simple queuing service, SQS, as another spout in the topology. A lot of times you also see it being tied in with a NoSQL database. That could be any number of NoSQL databases. We've seen examples where people have used it with Cassandra, with HBase, with DynamoDB, of course with Aerospike. So you see it being used with NoSQL databases to store state. You also see a lot of times where it's being integrated into a Hadoop environment, where you have this nice complementary nature between doing batch processing in Hadoop and real-time processing in Storm. And actually Nathan has written nicely about that in about what he calls the Lambda architecture. So he's got a book that's still an early release that talks a little bit about that, and that codifies some interesting principles that we often see as well in terms of what's the interplay between the real-time calculation and batch layers of processing. So you have this overall architecture. You have events coming in. You are doing some amount of processing, filtering of them in Storm. You're writing some results in two places. One is writing the raw events, maybe lightly transformed or augmented or decorated into a Hadoop distributed file system where ongoing batch processing can occur. Then you're also doing some near real-time calculation to be able to respond and update a NoSQL database so that it gives you the ability to have quick response to data as you're responding to the user. So that kind of overall architecture is a common one. Drilling down, you see integration patterns like this, where you might feed in a variety of different data sets. We won't go through the specific data sets here. We'll talk about this case a little bit later. But the notion that you might ingest data from a variety of different data sets that are coming in at different frequencies, do some amount of real-time processing to allow immediate response to a user, to feed a real-time search, so power search indexing, perhaps also to feed in analytics system, MPP database, and that there's often the interplay of some amount of work that's done in real time. In many cases, you can make some interesting compromises that the real-time processing can be approximate best effort. It's got to be done quick, but it may not be perfect, but that you can then clean up later on and have a more accurate final answer that's done authoritatively in batch. So that's a really powerful part of the use of a real-time processing system, is you can get it close to right and then have a final authoritative thing that cleans up and produces the exact right answer, right? And there's not only is that useful for simple analytics, counters, numbers, what's going on in the system, like how many events have I seen in the last minute, but it's also really useful for machine learned models. So if I've got a notion of here are the characteristics that lead me to recommend a given piece of content for a user. I have all the history of that user since the last time I ran a batch job, maybe overnight, and I have generally a notion of what are they interested in. But then they just came in and they viewed something else that I didn't expect. Well, I need to update my model based on they're obviously interested in this category I didn't know about, so I need to add that to what I already knew. So update my coefficients of my machine learning model to change what I recommend to them. So that's a great example of where I would blend some real-time information in scoring a model to make recommendations to somebody. Being a little bit more concrete here, thinking about some of the architecture for analytics, one of the projects we'll see, we had a web application where we had impressions coming in, and we started with a simple bot annotator. So we were trying to say, we want to apply some rules to say, do we think this web interaction is really coming from a human being, or is this showing the characteristics of it being a robot, and I actually don't want to count it, right? If you've done work with web analytics, and you probably know that there's a lot of activity on the internet that's generated by robots. Some of it's polite and it's pretty easy to catch, like it has the user agent of Googlebot. Others of it, maybe not quite so polite, but there's some other telltale signs that might give you a clue, right? So the notion was feeding in data, doing some basic annotation, then writing that data out to Hadoop. The idea of having some light transformation analysis of it being done in Storm before writing it to Hadoop meant that you had a consistent rule, and you kind of know at the time that the event came in what your perspective was, whether it was a bot or not. Then that got fed into a downstream bucket bolt that's really designed to come up with a time series to say for this period of time, what's the number of impressions, right? So have a window in memory, basically, and periodically flush that out into the NoSQL database to say, let me update that and give an update for what's the number of impressions I've seen in this given time window, right? So, and that then allowed the system to take that data, and you had a real-time view, but then you also had the historical view was no longer in the NoSQL database. You didn't need to keep years of history to know what were the number of impressions that, say, this piece of content had. Most of it was just sitting in Hadoop that you had done MapReduce jobs and over time computed authoritative counts of activity. But you could combine that in real time into a system that would take both the batch and the real-time version and provide information. So, and in fact, that along with some parameters that were created from a machine learned model that was trained in Hadoop were applied in real time in a web server in this case to predict the number of impressions in future. So taking the historical time series and some metadata characteristics of the content that was known allowed applying a model that was written in R that would apply in real time to say, what do I think the future number of impressions of this piece of content would be? Right? So this was for a specific publisher that wanted to have a kind of futures model of how many impressions would be going forward. So high level, you had this notion of combining batch analysis of a massive historical data set with timely updates of the recent past to drive real-time predictions. So that's a kind of advanced predictive analytics approach of what you can do with this kind of architecture, blending Storm and Hadoop. So here, in this case, we'll see a little more detail of, the historical data set was being stored on Amazon Web Services and S3. The analysis was done historically using Hadoop, specifically combining Pig for doing some basic processing with R for statistical modeling. And then in the use for recent past, the processing was being done in Storm. The local state was being stored in a NoSQL database. And the analysis was being done in R, where a web service was basically pulling data from that NoSQL database and applying an R model in quickly. So stepping back, this was a kind of recommendation system. And it's worth looking at what's a common architecture for a recommendation system, and how does Storm maybe fit in, right? So if you didn't have Storm, a common real-time recommendation system might look like this, where you've got data coming into web servers, you've got a batch feed of data into Hadoop, you score that, you push the model back out to update your NoSQL database, and then anytime you've got an event coming in for a piece of content, you update some coefficient in your NoSQL database, and you read the value of that coefficient and scored it, right? So in a sense, that's a fairly straightforward key value problem. You don't necessarily need Storm. Where you start to see it getting more interesting is, what if I start to have pressure where there's too much calculation to do to just do it inline in a single thread on this server? I want to distribute it out. And that's where, in this example, what we did with one customer in the advertising space, the publisher specifically, we were able to do that. So just a little more detail here. Again, we were using spouts from Amazon, simple queuing service, SQS. We had both events, so impressions are an example of events, so it was clicks, as well as commands, activity that was going on in the system to change behavior. And both of them were being fed through to being written out to S3. In the case of the events, they're being annotated with, do I think this is a robot or a human being? And then there were also performance counters that were being updated. So the performance counters, there were sort of two notions of feeding the event counts through. One was a performance counter is like for all of time, how many times have I seen this page? And then the time series one said, what are the windows, right? In the last hour, in the previous hour, how many times have I seen this particular event, this impression, this click, et cetera, being written into a NoSQL database, in this case, DynamoDB. Right? So that was that's a simplified version of the Storm topology. So wiring that together, what you get is this, which is instead of having to have the web servers do all the updating work in the NoSQL database in a single thread and synchronously, you distribute all that update work that goes into making the model work across a network of processing elements, and you decouple it. So when you need to apply the model, you read it quickly out of NoSQL, and you answer. But when you want to do the updates to change the state, you divide it across many elements, and you've got a scalable system, so you don't have to worry about any delay, and you have a better ability to get it done relatively quickly. So that's parallelizing updates. In fact, when you think about it in a recommendation system, it's not just updates that you might want to parallelize. It's the asynchronous updating of a model that can come if you want to update many time series from a single event, or a single event updated many items that you wanted to change your recommendation view on. But in a more advanced case, you might want to score many items even on read. Right? So if I want to do something like a lookalike model where I don't have state from a single thing that drives my model, but I want to combine, I have a multi-dimensional model. I might want to know something about the user and the item and the context to recommend something to them. It'd be costly to pre-compute all the combinations of those. So instead, I have to do more work to take information about various elements and combine them. And there, I might not want to wait for a single process, a single machine to do all of that work to analyze and come up with a score. If I can divide it over a network and get an answer, I can more reliably compute it faster, right? I can share a bunch of processing power, divide up the problem, and get a faster answer, right? So using Storm in a recommendation system is often used to update the model that you pre-compute the recommendation information, but sometimes it's good even just for making it fast to give you back, to calculate the read and computation to scoring as well. So that's a little bit about one important class of use case, the use of Storm in a real-time analytics system where you're trying to do predictive analytics to make recommendations. Let's take a look at another somewhat related use case, another project we did. This was more of a targeted user scenario, trying to understand the kind of users that are interested in a given kind of offer. So a little bit different, more in this case, we have the notion of an offline profile of the user, some of their activities, and an online profile, trying to put that together. In this case, instead of using SQS, the Bolt was based on Kafka. So that's as I mentioned before, it's a scalable messaging system that's highly resilient, retaining data. In this case, data was written directly from Kafka into Hadoop, and then in parallel fed into Storm for stream processing. And here, one of the interesting things is the data was being used to update an index to be able to quickly find users. So as the events were coming in real time, you're able to do updates to a search engine, in this case Elasticsearch, and based on doing things like often you have a more complex record, you want to do some amount of joining of some metadata that's being held in a NoSQL database. You want to be able to do things like project out certain fields of that user's activity that are worth putting into the search index. So you don't want to have, it's not the full record. You can do things like having a link to where it is in stable storage, maybe in HDFS, maybe in a NoSQL database. You can attach that pointer to the search record. So if you find it and you don't have the information just in the search entry, you can look up more detail in a backing store. You can do that. So all of these things are examples of where you want to apply some logic to do indexing and to be able to do it in low latency. And the last thing is Elasticsearch is pretty good at dealing with streams of small numbers of updates, but more traditionally, alternatives like Solr really don't do well if you do updates of one record at a time. So the ability to have small amounts of micro-batching in Storm, the ability to buffer up in memory a few records at a time, maybe 1,000 or 10,000 records, and then flush a small batch out to the search index or after a certain amount of time is powerful as well. So it gives you a little bit of buffering in the architecture. So another example to think about that we've seen is using Storm in smart energy, right? So in this case, again, this notion of being able to use Kafka to ingest data from a variety of data sets, meter and sensor data, combining it with some radically different data like geographic data, weather data, energy production data. So you've got all of these different data sets that are coming in at radically different time scales. But as data is coming in real time, you want to be able to respond, right? So you want to be able to, again, parse and filter the data to be able to join it together, look things up. So you can often have some interesting affinity by having a notion of common fields. So it's in the same area, it's the same customer, so I can have a single instance of a bolt that's holding in memory some useful information. So it gives me a kind of interesting way of joining data together, as well as some confidence that while I don't have a transaction in my NoSQL database, I can kind of consistently write data to multiple tables with the same key because I've used the fields to identify a single bolt instance that's going to write correlated data. So it gives me some interesting capabilities there. And that lets me, again, write data for search purposes, to Hadoop for batch processing, to the NoSQL database for data serving, as well as potentially archiving. So again, in the smart grid case, this can drive a number of interesting analytic models, right? You could do things like predicting outages, looking at grid problems that you predict problems before they happen. So there's do alerting, and it also is nice that because you've got information that can be held in memory, the hot things that are recently changing, you can use a distributed RPC paradigm to go out to those same bolts and pull data that's likely in memory to get information about what's going on and quickly assemble results, right? So it gives you some nice caching properties as well. So that's a little bit about using Storm for energy grid management. One of the places that we see a lot of interest of using Storm that's radically different, that's quite different than its origins in more web systems, is actually for financial systems that are around trading, right? And in a sense, maybe that's not surprising because you've had complex event processing grew up in Wall Street, and that was its initial niche. And they were the only people that were willing to spend the kind of money to have proprietary systems to do this kind of thing. So an architecture there can be blending market feed data and order management data, that you use Storm to put things together, reduce it to a usable subset, and push data into a NoSQL database that then you analyze more deeply to understand what's going on. So at a high level, that's a kind of flow. Unpacking it a little bit, you can see that the common requirement is market data. You can have millions of messages a second, and there's usually a fair bit of work to do in terms of filtering it and aggregating and averaging things. So there's a massive flow of data. And again, this is not a system that's being used in Wall Street with a notion of, we're going to use this for high-frequency trading, get to an answer in nanoseconds. But you want to be able to have fairly up-to-date information about this massive amount of information, right? So trade compliance monitoring or looking at pricing of execution efficiency, how much am I paying, how efficiently am I executing trades, is a great example of something where you want to be able to compute this sort of thing within seconds, minutes of activity happening. It's not acceptable to say, let's see after I've executed a massive trade the next day how I did. There's a demand by customers to have accountability and understand what's going on during the day as these things are going on. Right? So you often have a need to incorporate both reference and static data into the system. And it's complex, right? You have to be able to look at what's going on by a specific, what stock it is, or what other instrument it is, what time window. You have a need to have some amount of buffering. In some cases, you get to interesting complex state that the state in the market is not really just, like for looking at transaction pricing, you can't just look at something simple like what is the bid ask, for those who know a little bit about stocks, what is somebody offering and what is somebody to sell at and buy at? Because you actually have to look at, well, what's the full set, the full order book? What are all the different offers that I have? Why? Because I might have very little volume right around the trade price, so I don't really have a good buyer that could absorb meaningful amount of a more meaningful sale at the best price. I might have a much worse price where I have a meaningful bid to buy a large amount of stock. So net, you have to do analysis of a much more complex large data set that's changing over time. As trades happen, things pop off, trade orders get canceled, et cetera. So maintaining that and being able to apply a model in real time where you've distributed across nodes that represent this given stock, this given time frame becomes important, right? And there's a variety of uses of this. So I talked about trade efficiency. There's other things like finding strange trading behavior for trade surveillance, et cetera, right? So you can have needs to have alerts where things are working badly and raise a flag that something's wrong, as well as ability to kind of reliably pull statistics out of a computation cluster with a distributed RPC. And one thing I thought was interesting is one of our customers was interested in using a scalable streaming technology, and they were looking at an alternative commercial software package. And they found that when we did spend a little time with them tuning the performance of Storm, it was about half the throughput that the expensive commercial software achieved on the same hardware. But when you actually looked at price performance, Storm is about 25 times better total cost of ownership, right, is the cost of that other software. So, but I think just as importantly was the notion that it could scale to the demanding needs of dealing with peak volumes of trade data during, as you can probably imagine, trade data there are massive spikes, and you have to be able to design a system to account for processing millions of events a second in a spike. So, overall, a few lessons from some of the different projects we've done with Storm. I mean, it's still early days. It's a newer technology, but some nice qualities to it. It's overall well written, and we've had some good experience with it. And I think that's why it's gaining traction, why so many of you are here today because of that. We found that it's easy to develop, but it's certainly, like many distributed systems, it's hard to debug. So starting locally, writing good tests, making sure things are working reliably before you scale it is super important. That timeouts can be a challenge. That we've run into cases where you'd have infinite loops of failure, where you would try to process something and there'd be a bug in the code, and it would get rejected and thrown back into the queue, right? So you could keep trying to reprocess something that's doomed to fail. So one example of a way of handling that, what we did on the first project was we used memcached to keep track of how many times had a given tuple failed, so that we could eventually give up and say, I'm not going to fail it. I'm going to say it's just not going to work, and I'm going to dequeue it and say it's acknowledged. This is still never going to work. It's a known failure, right? So rather than having that infinite loop. When you're working with the lower level primitives in Storm, it's sometimes hard to handle it, dealing with how do I get things to process exactly once or at least once, right? So there's a variety of techniques. You can use higher level abstractions like Trident, where it's built in for you. You can apply some patterns. There's also approaches where you can write redundant data and simply repair it after the fact and know that, well, I have 2 copies of this data and I've got a unique identifier. I'll clean it up after the fact. So depending on your use case, different trade-offs can work. I know that on the first project we ran into some issues where performance counters weren't getting flushed out. And that caused us some problems as well. Another thing is that generally it's a good idea to be acknowledging your messages. While it's nominally optional, things work a lot better and performance is a lot better if you do that. And a number of ideas in terms of how do you batch data. One of the things we felt is a lot of times if you've got different timescales in your system, that it's valuable to instead of using, say, NoSQL, a lot of times the queue is a lower cost abstraction where I might read something and process it, but if I want to buffer up data for an hour, I might push it into a queue and then have a larger set of data that I read off that queue that says, here's all the things that happened in the last hour. So queues can be an interesting way of absorbing larger amounts of data, especially if you've got something scalable like Kafka, that you can feed output from one bolt and then read that queue from the next bolt to process it. and again, the different ways of batching to stable storage, S3 or HDFS, depending on whether you want to clean it up afterwards or rely on higher level abstractions like Trident to buffer up the events. So those are a few of the lessons from what we've done with Storm to date. In conclusion, there's a number of different real-time problems. Some of the simpler examples of processing real-time, you probably don't need Storm, right? You can do stuff with a NoSQL database and just read and write data, applying a model, doing some simple counters. But as you start scaling, the ability to have a distributed grid that does the processing, that lets you divide work up across multiple machines, that uses memory across multiple machines to hold state, can be powerful. And it can really integrate in with an overall big data architecture, including Hadoop and NoSQL and scalable queuing, and provide some great value. Right? So we see the technology as complementary, and we think that over time, more and more big data architectures will include Storm for real-time processing of data. So with that, I guess I finish with just, again, a reminder, we're hiring at Think Big, and people interested in working with Storm and some of the other big data technologies, we'd love to talk to you. And with that, now turn over the floor to you for any questions you might have from my presentation.
Thanks. I guess a couple questions are kind of related. If it's written in Java, how do you avoid hiccups during garbage collection? And sort of the flip side of that question is, how predictable is the real-time performance? How consistent is it?
Sure. So, I mean, I think a couple of elements. One is in terms of dealing with garbage collection, there's always a lot you can do in Java to tune your garbage collection, and you want to tune it to minimize pausing, set the right heap sizes, have the right amount of liveliness in the garbage collection. And also some of it is being careful in your code not to generate lots of unnecessary garbage as you write your code. So you can code in a way that avoids problems. But at the same time, I think it's fair to say that the Storm isn't designed as a hard real-time system, right? It's being designed as a system where things happen relatively fast, where things happen on the scale of hundreds of milliseconds is reasonably reliably, but not that you've got a system where you've got a guaranteed response time to how data flows through. Yeah.
Some of the commercial competitors to Storm?
So what are some of the commercial competitors to Storm? So there's been a whole class of more traditional complex event processing systems like Streambase that were less scalable. So that was one wave. You've got technologies like SQL Stream that are SQL-based commercial streaming technology. You've got IBM InfoSphere Streams is another commercial competitor. You're also seeing some emerging different approaches, whether it be something like H-streaming that's doing streaming in a Hadoop architecture where instead of having MapReduce that ends, it sort of has a MapReduce that just keeps processing streams of data. Also look at, there's a similar kind of streaming processing paradigm inside Continuity's server as well. So they have a Yarn-based implementation of something that's a streaming approach like Storm, and they're also commercial. So those are a few examples. There's probably others that I'm not thinking, but those are the better known ones. Yeah.
How do you manage deployment?
So how do you manage deployment? Well, that's an area we've definitely put some effort into in terms of using Puppet and writing some standard scripts and approaches so that it's easier to reliably configure a machine that's running Storm that can execute, have all the right pieces and be configured consistently. So that's an important part. Certainly there's some management tools in Storm. I think that's clearly an area where there's meaningful value to have commercially in terms of having higher level tools for managing it. I think another part of that answer is, will Storm continue to be run in standalone, or will it start to fit in under technologies like Yarn, which is a more general grid resource manager in Hadoop, or indeed Mesos, which is a kind of competing resource manager that is also being used for some big data systems with Hadoop.
So, so if you have like n number of nodes running Storm, the number of connections among them is like an n squared. Like everybody has to be connected to everybody to pass on messages from a single spout, or how does that work? I haven't seen a clear explanation on the tutorials I've read.
Yeah, so I believe, and I'll defer to Troy, who's one of our engineers, to make sure I get this right, but I believe that, that it's going to depend on what the actual pattern of communication is, right? So if you had bolts that were only talking one bolt to one other bolt, it wouldn't need to be n-squared, but of course, in a general case, a topology could have any node talking to any other node, and then it would be n-squared.
Zookeeper is used for coordinating the various nodes, and they're definitely not broadcasting to all the other nodes. So it basically follows the flow of the topology. So you have distribution, but with a certain bolt, you might fan out to say 10 bolts, and those would be spread across the various machines, and that's the only flow of data that you're going to have.
Right. So in the worst case, if you had one bolt talking to all the other bolts, then you could have n-squared communication, right? But it doesn't have to be.
So if you have to use Storm along with Hadoop, so do you think it's a good practice to share the same cluster where the same Storm nodes can act as the same nodes are there in Hadoop, or do you think you could have them separate and so that they don't overlap with each other?
Yeah, so it's a good question. I mean, I would say that the first thing is that in general, in current technology, we don't typically see people deploying Hadoop in the same place where they're deploying a real-time serving system. So Storm tends to have affinity with the real-time serving system where you've got things like web servers, app servers, NoSQL databases, search lookups, right? And those tend to be distributed across multiple data centers and coordinated with eventual consistency. Whereas typically we see Hadoop being used more of in a core analytics world where you're doing kind of deep archival, longer-term batch processing, training machine learning models, simulating things. So in that world, you would tend to run them separately anyway. Now, there's certainly efforts to make Hadoop have more relevance, and we know of companies that are deploying Hadoop-based technologies like HBase out on the edge for edge serving, right? And in that world, you could run Storm on the same machines, right? So the project at Yahoo, where they now have contributed code to have Storm run inside of a Hadoop cluster with Yarn, allows that possibility. I'd say that's still pretty experimental, right? In order to do that, the thing is you have to think about how much control do you have of the resources between Storm and MapReduce or other things, right? So generally for real-time processing, you want to have pretty good confidence that you're going to have the resources you'd expect, and that means having kind of arbitrary access to data or CPU utilization by batch processing would be problematic. You'd want to be able to carve out at least some amount of resources that are guaranteed. So I'd say that there's interest in making them coexist, but today it's not a common practice. Yeah.
So how does this compare with SPARC?
So how does it compare to SPARC? Well, so SPARC is more of a lively system that's written in the MapReduce style, right? So I'd say that fundamentally, I still think of SPARC as something that's, while it's better written for having some memory caching and lower latency interactions amongst nodes, it's really still designed more as a compute one thing and shut down model rather than a streaming model of ongoing computation, right? So people are using SPARC for things like iterative machine learning models where you might have lower latency to communicate, but it's not being used, to my knowledge, in an ongoing streaming mode.
In Storm, do you have the concept of a transaction? If so, how do you manage transactions across distributed nodes?
So, Storm does have this, at least the notion of being able to acknowledge an event, and so you can read from a spout and only confirm and remove it when you've completed your processing and your downstream bolts have all confirmed that they've processed the data you had. So in that sense, you have something like a transaction that you had a flow and it had to go all the way through the flow, and all the downstream processing triggered by something gets acknowledged and dequeued. So in that sense, it's like a transaction, but it's not a complex transaction. You can't have coordination between two separate events coming in from a spout and saying, well, now we're going to do a two-phase commit, and when both of them get processed, we're going to commit it. Yeah.
What was your most challenging debugging situation and something that really caused you to lose sleep and stuff, and how did you go about it?
Sure. Well, I think it's a good question. Maybe I had some examples here. I don't know, Troy, if you want to elaborate on like some of the timeouts or any of the other areas. Maybe I'll pass the mic if Troy wants to answer that one. Put you on the spot.
Let's see. I guess obviously anything when you're highly distributed and things are going wrong, then it's nice if you can pull it back to the local mode and try to test on the same machine. Let's see. Beyond that, if you're not too familiar with Clojure and things are starting to go haywire and you're having to if you're trying to step through a debugger and hop into Clojure code, it can be a little challenging. But you can build test fixtures around individual spouts and bolts, so you can kind of be assured that the individual components are working okay, and so you can usually avoid things. It's usually around the strategy. If you can build a strategy for testing, unit testing properly, getting the topology to work in local mode, you should be, you're fairly good to distribute it. Beyond that, it gets into collecting metrics, so you know how the traffic is flowing through the network, through the topology, and sort of monitoring that and being able to work with that. That's where it gets challenging, I guess. So it's not really debugging. It's really more like as traffic is going on, you want to get a better sense of how your topology is operating.
So it seems like you really haven't so far had to deal with a situation where like it went on for days and people couldn't figure out what was wrong. So it's not.
No, nothing like that. So.
A couple of quick ones. So, what are the basic bottlenecks within Storm? So, if you want to go to the sub millisecond or do high frequency stuff, what is it that essentially prevents you, or is it just sort of tweaking and fine tuning and sort of migrating into more expensive stuff? And secondly, where does parse stream fit into?
So how does what fit into it? The second
parse stream.
Parse stream.
Right.
Okay. So on the first one, from my understanding is that there's a number of elements where you've got distributed message passing, network latency. That while Storm uses 0MQ under the covers, it's reasonably fast. That still, as you think about the nature of the communication, that there's enough latency in there that it's not well tuned for sub-millisecond. I haven't profiled it to say, well, it's exactly here, right? I mean. But I think that in general, it's not really a design goal, and so it hasn't been. If you don't tune your code carefully to get down to that, especially in a distributed system, to get down to that level of latency, you're not going to do it by accident, right? So that's one thing. In terms of parse stream, I've heard of it. I'm not terribly familiar with parse stream. It's a commercial technology that there's when asked about competing commercial technologies to Storm. Your question reminds me that there's a lot of others that are maybe a little less well known, but there's certainly a lot of people that are working on various forms of commercial streaming technologies of one form or another, whether they're Storm-like or have other characteristics.
How do you monitor your topology? So how do you keep track on what each bot is doing and how long that bot has been running on a particular worker? And do you track all those things?
So how do you keep track of what's running in your topology, how long it's been up, et cetera? And I think out of the box, Storm has some information about that. I know, Troy, if you comment, you did some work on.
Definitely the administration web GUI has a lot of information there, but you also need to, like any distributed system, you need to add your metrics and logging appropriately, and then aggregate your metrics. So that's usually the main way to do it.
Is there any particular system you recommend? For example, when I write my topology, generally I will output a bunch of parameters, keep track on, for example, how many tuples has the number, for example, value greater than a certain number, and how many invalid records.
There's a variety of metrics variety of different metrics libraries for aggregating metrics.
Where do you output those metrics? How do you collect this? Do you use
JMX?
Oh, no, no, no. I mean, where do you store those metrics?
Well, there's different strategies. Some will pull the metrics and put them into a NoSQL database, and then you just track it through that.
Right, so like Cassandra has counter support that makes it easier, for example, is one approach. Okay. Yeah.
So I had a question regarding how do you deal with Storm and the co-location of data when you have a large set of like multi-dimensional data in tuples, and like you're doing like real-time calculations on data that might be spread across different sets of nodes.
Mm-hmm.
So what techniques do you use for that?
And so it's obviously going to vary a little bit by your problem, right? So there's cases where you might have a topology where you pull data from different nodes, and in getting the request, they each kind of contribute the piece that made sense for them, and then pass it on downstream to a next phase bolt that combines them to produce its result. So that's one example. There's other cases where you might read data from a NoSQL database where you can certainly read data from a NoSQL database from different places, right? So, I mean, it's going to vary a little bit based on the specific problem you've got.
But don't you want to like reduce network bandwidth? And if you have like, let's say, 2 bolts and the data spread out across different nodes in your network,
yeah.
That's going to slow your calculations down a whole lot.
Yeah, so I mean, I guess ultimately the trade-off is if you want to have data co-located in all combinations, you can do things like make sure the data is already in memory in the different places. So there's various tricks you might play depending on the nature of your problem, right? If you had small dimensionality for one thing, having that information on all the nodes could be faster, right? So it's really, or you might have store data around each combination, right? Or might have also some form of caching, whether it's just holding things in memory, whether it's having a NoSQL database where recent entries are likely to be in memory cache and faster, right? Any of those techniques could again speed things up, but it's going to depend a lot on your specific problem. I don't think it's a one-size-fits-all answer there.
You can also do a join in a topology. You can join 2 streams together. As long as you have the cardinality is low, you can keep a buffer within a bolt to sort. It's kind of like a map side join where you can get to if the cardinality is low, you can do that.
So my question is, usually for financial data, it will require like ASIC compliant. So, but in your use case on the financial data monitoring compliant, and do you run into the issue of eventually consistent issue?
Yeah, so I mean, I think one of the advantages of a lot of the kind of scenarios where we see people using this kind of Storm for real-time calculation is that it's a little more forgiving than something like trade execution, right? You have to have absolute confidence in accuracy and correctness in trade execution, and eventual consistency isn't good, right? I mean, you need to have a very different standard in a case like that than in a case where you're trying to heuristically identify anomalous behavior or give people some visibility into efficiency of trade execution where it's not regulated, but that there's a lot of value in being able to provide an answer more reasonably. So I guess the summary is that it's a case where you've got a little more leeway than in some of the other financial use cases.
So in the programming models, which one you prefer? Which one you use normally? Is it raw code or Trident?
So what do we use more? Raw Storm API or Trident or some of the others? I'd say we've done projects using different ones in different cases. In general, I think you see the higher level abstractions like Trident are powerful and valuable, right? So if they work for you, a lot of times you see companies preferring that to working with the lower level APIs, but it's good to always have them there. So my feeling is that Trident and other DSLs are going to be more prevalent than the lower level APIs. But it's still early to tell. so what are the technologies that are typically being used for ingestion? We see there's different queuing systems. So, Kafka is one that we see often being used. Certainly, Kestrel that was used at Twitter is one that's used. SQS on Amazon is a queuing technology. Flume is another one you might see being used. And a variety of other just message queuing systems. RabbitMQ, ActiveMQ, all are ones that certainly can be used. So
can you compare Flume with Kafka?
Yeah. So can I compare Flume with Kafka? So, Flume is a system that's more designed just to load data into. Ultimately, it's designed to be a scalable fan-in system for loading data into an end system. And Kafka is a more general queuing technology. I mean, Kafka's definitely got more features built in for things like replication of data for high availability in all scenarios. So that I know Kafka is being used at pretty large scale at LinkedIn. It's also got a little bit of a different model in terms of it's more of a pull model from a client instead of a push model that Flume has. Any more questions? All right. Well, thank you everyone for coming. It's been an honor speaking.